uncertainty forecast with Python. And the motivation for our research is that, firstly, the Texas Water Development Board is still using TextPlan, a first generation 2D hydrodynamic model. So they want to make a change to a newer 3D hydrodynamic model, which is SciPy. So in this research, we're going to use the SciPy as our hydrodynamic model. And also, HTWDB creating an OSPU forecast requires manual intervention at each steps. For instance, to download the web data and transfer the web data into the hydrodynamic models formats, and then to initiate the hydrodynamic model, and then finally to configure the hydrodynamic model's outputs for later analysis. All of these steps are need manual labor. So in this research, we're gonna use Python to develop a totally automatic wrapper, to wrap all of this process together just in one step. So we also made a further step to analyze the hydrodynamic forecast uncertainty. So why we have to do this? Because any OSPU prediction are based on the forecast data, and we all know that any forecast data are, just contain some errors. We can also say that the uncertainty. So when the hydrodynamic model uses the forecast data, those errors may transfer to the hydrodynamic models. And eventually, those errors or uncertainty will transfer to the OSPU predictions when the OSPU model uses the results from the hydrodynamic model as its own input. So the research objectives of our research is to build up a wrapper system like this. So we call it HyosPy, which stands for Hydrodynamic OSPU Modeling with Python. So basically, we're going to use Python to develop a sequence of hydrodynamic models, and along with the initial OSPU conditions such as time and locations, we can use the OSPU model to do the simulation, to make the OSPU prediction. Right here, currently, the GNOME, like Dr. Barker said, that there is no Linux version of GNOME, right?
There is now, as of like 2 weeks ago.
Oh, yeah. Yeah. So in the meantime, we write the RK4 OSPU transfer model by using Python to ask a replacement. So we cannot use that one, right? For the OSPU. And as the outputs of the RK4 model, we can visualize the different OSPU predictions on Google Earth by using Python to edit a pre-written Google Earth JavaScript module. And also, we can use the output from the RK4 module to estimate the uncertainty in those multiple OSPU tracks. So here is a chart to show us how the multiple model works. At real-time 0, the first selfie gonna initiate with 0-hour hindcast data and all of the forecast data, which means that this selfie gonna run in a completely forecast mode. And then after delta t start time, the second selfie gonna start with the latest available hindcast data and the corresponding forecast data. And then after another delta t start time, the third selfie gonna start with the latest available hindcast and forecast data. So this system is just like a sequence, and it goes on until the last selfie finished running. And obviously, the difference between these multiple models can provide us some insight of how the errors, or we can see that uncertainty, will finally transfer to the this end. I mean the OSPU prediction, right? So this chart shows that how we use Python to implement these ideas. So basically, we use Python to develop a master wrapper. So this master wrapper works like a central control system, which means that we can set how many models, how many hydrodynamic model right here, we use selfie, right? How many selfies we're gonna run in a sequence, and set the time interval of each selfie, and also it works like to connect each model in sequence. And for every single selfies down here, we use Python to develop a module. And this module works like a, like a automation machine. And this machine works to, to automatically download the web data and transfer this web data into selfies input formats, and then, initiate the selfie with this latest available data, and then after the running, it will automatically configure the selfies outputs for the later analysis. So all of these processes are automatically done by using Python. And our wind data are obtained at Texas A&M University. The raw data format look like this, and we use the formulas down here to transfer the data format into self-input, where the 0.447 is just a unit convention from mile per hour to a meter per second. That is the selfie standard. And our Thai data are also obtained at Texas A&M University at Tikkun. The raw data look like this, where the black curves here represents the matter tidal elevation, and the blue curve represents harmonic tidal elevation correspondingly. To generate the forecast series of tide, we use the formula right here. Basically, we're gonna add the harmonic tide elevation to the mean difference between the measured tide elevation and harmonic tide elevation to a certain time period. So in this case, we're gonna choose this period to be maybe 24 hours from April 20th to April 21st. This is gonna guarantee that we're gonna have a smoother transit from the hindcast data to the forecast. So here is the result that shows the generated series of the forecast. So the yellow curve right here represents the forecast tide we generate by using this method. So it's pretty good, I think. Like I just said, at that time, there's no Linux version of GNOME, so we use Python to develop a RK4 surface transport routine to be a replacement of the HyosPy model. So basically, this RK4 model will compute transport of the HyosPy over ranges different positions, and then it could also compute tracer movement for different hydrodynamic simulations. I mean, it could, to compute multiple running in just one time. And the most fun part is that it could visualize the different HyosPy tracks on Google's by using Python to transfer all of the coordinates information to a pre-written JavaScript, and then finally to form a HTML file to have all of the information on it. So finally, we used Python to evaluate the hydrodynamic forecast uncertainty. Basically, we use Python to calculate the different distance between the predicted particle positions at each time step for the multiple different simulations. And then we use Python to calculate the two uncertain measurements. This here we choose the very simple two measurement, which is the mean distance and root mean square distance. And we're expecting to have a relationship like this. So before the forecast horizon, the uncertainty will increase very slowly. And right after the forecast horizon, the uncertainty will increase sharply. And this here, it is an example that shows the simulation of HyosPy with an HyosPy event that is definitely an imaginary HyosPy event at the starting point right here. And the numbers of selfie we use in this example is 12. And for each step, we have 13 particles. And the simulation period is 48 hours from May 18th to May 20th. And the time interval for this system is 4 hours. So we can see from this figure that, in just one HyosPy event, we have several different HyosPy tracks, right? Several different. We can see that the different colors dot here represent different HyosPy tracks, HyosPy predictions. So this figure, this simulation just proved that the errors we have in the forecast data are going to transfer to this end, to the HyosPy, right? So we use Python to quantify these errors or the uncertainty. The result looks like this. I think it's a good result. We can see that at the start time, there is no uncertainty. And maybe after 5 hours forecast time, the uncertainty is going to increase very slowly. Maybe after 8 hours or 9 hours, it will increase very sharply. And then it's going to go stable in the after 40 hours simulation forecast time. So conclusions, I think I'm doing so quick. So we have developed automated hydrodynamic model wrapper, and we use Python to develop RK4 surface tracer routine, and we can use this model to visualize HyosPy predictions on Google Earth, and we also do the uncertainty analysis by using wrapper, and all of this gonna provide some insight of how far in the future the hydrodynamic model can be trusted. So acknowledgements. Firstly, we want to thank the TWD personnel, Dr. Dahars, and Dale and Solomon. And also we want to thank Dr. Joseph and Dr. Chris Barker right here. And also we want to thank Itai from Stanford University, who creating the first generation of Python wrapper. And last but not the least, Dr. Paula Pasaloka at UT Austin. All right, thank you guys. Yep.
Do you have an idea of how long you starting the model with the fresh data? You get data, because then we could get some comparison of the hours different. Are you doing it every 3 hours or every 6 hours?
Yeah, you mean the wind data, right? The refresh of the data is 3 hours, and when we start the system, it's gonna automatically download the data from the website. Yes, it's all of things that automatically down.
Correlates to the wind data.
Yes, yes.
Can you go back to that slide and just like the and just
This here.
yeah, could you tell me more about it? I'm having a hard time
Oh yeah, I can show you the code here. So we use Python. This here, this is a JavaScript module. And when we use Python to calculate all the predicted coordinates of the particles, and then we use Python to transfer all of this coordinates information to the location, and then it's gonna make a HTML file. That is the final result like this. It's gonna show you the particle tracks on Google Earth.
So each one of those is a track and the color is from a model.
The different color dots right here represent different predictions. We have several different predictions, right? Because we have 12 selfies, which means that we have 12 HyosPy predictions. Every hydrodynamic model gonna result in a HyosPy prediction. So,
So you're finding different user recordings, so some of it goes wrong and some of it
yes, ma'am.
Just follow up on that. That means a lot of that area that has a bunch of overlays symbols that we're seeing just one depending on the order.
Yes, I mean, each prediction will, for each prediction, the next step is based on the previous steps, right? So that is how it works. I mean, that's the hydrodynamic model itself. Its work itself. I mean, we just build a wrapper, and the wrapper just like a interface, to connect every step, and it gonna the first step down, and then the second step, and then the third step. So.
There's a really good PhD thesis by one of Hodges' other students a couple of years ago, which shows how very tiny errors in the initial predictions accumulate in partial tracking. So it's better to do kind of aggregations rather than looking at that.
Yeah. Excuse me, I can't hear you.
What flavor of uncertainty
The uncertainty, we just, we use this here. We just use these two simple measurements. The one is mean distance, and the other is Rubin square distance for a comparison. I mean, to it's based on the assumption that every prediction and I mean every prediction is equal with each other, because gets the web data, and the web data just got some errors or uncertainty, and every prediction is based on this data. So we use the mean distance or the mean square distance to be a measurement. That is based on the assumption that we just said every predictions are equal. Right.
Follow up, you're just doing a single particle release from a single place.
Yes, a single particle. Right.
So have you done any work with different star positions and see if that greater or less uncertainty depending on where the particle is?
We have tried that. It's just shows some similar results. Yeah. So I think it's just a preliminary method to show the uncertainty. We're gonna develop more detailed and more comprehensive method to do that.